In Chapter 7, we're going to start looking at alkyl halides, and then we'll start looking at our first reactions and reaction mechanisms, which are going to be the nucleophilic substitution reactions. So to start with, we can classify alkyl halides. Similarly to how we classified carbons and hydrogens, and that's by what's bonded to them. So if I have CX, and there are no carbons on here, but they're all hydrogen, this would be a methyl halide. If I have one carbon and two hydrogens with my X group, X is just a generic for halogen. So chlorine, bromine, iodine, fluorine. X just means one of the halogens. So if I have a halogen bonded to a carbon and one other carbon, this would be a primary alkyl halide. If I have CX with two other carbons and one hydrogen, that would be a secondary alkyl halide. And if I have a carbon with a halogen and all other carbons bonded to it with no hydrogen, that would be a tertiary alkyl halide. And then if we look at alkyl halides near pi bonds, there are different ways that we can describe the alkyl halide. So if I have a pi bond, if I have a halogen on one of the sp2 hybridized carbons, this one is called a vinyl halide. So vinyl means that it's on the same carbon as a pi bond. If I have it on the carbon adjacent to that, this is an allyl halide. And this is going to be important as we work through organic chemistry. We'll talk about these different positions, and anything that's on an alkene, that's at one of the sp2 carbons from an alkene, is going to be considered vinyl. If the place alpha to that, or next to an alkene, is going to be allyl. We can have a halogen that's on a benzene ring. A halogen on a benzene ring would be called an aryl halide. So if we think about it, that's sort of based on the word aromatic. So an aryl halide. And if we have one on a carbon next to a benzene ring, this is called a benzyl halide. So again, we'll use the word aryl or aromatic to talk about a lot of things. So aryl means that it's on the benzene ring. Benzyl means it's on the carbon next to the benzene ring. And we'll use that terminology as well throughout the course. Now the first and the third ones, the vinyl and the aryl one, have the CX bond on an sp2 hybridized carbon. And because of that, they're not going to undergo the reactions that we're going to see this chapter. However, the allyl halide and the benzyl halide have their CX bond with an sp3 carbon, and they will react the same as the other things that we'll see this chapter. We're not going to do very much with these reactions with these different groups for this chapter, but we'll see them occasionally. So the hybridization of the carbon is very important in how these things react. So the sp3 ones will react, these sp2 ones will not. So as we look at the nature of the polar C to X bond, one of the things that's going to be important are the relative bond strengths of the different CX bonds. So if we think about it, it really just goes by size. C to I being the largest of the atoms that we're going to look at. We're going to look at fluorine, chlorine, bromine, and iodine. We don't really use acetine. So the C to I is the largest atom of those four, so it's going to be the furthest from carbon, which makes this the weakest bond. So then that's weaker than C to Br, which is weaker than C to Cl, which is weaker than C to F. This one is the strongest of the halogen bonds. And this is going to be important as we look at substituting one for another, because the Ci being weakest is easier to substitute with a bromine, a chlorine, or a fluorine. The bromine is easy enough to substitute with a chlorine or fluorine because they make stronger bonds, but not easy to substitute with an iodine, which would make a weaker bond. Chlorine is really only substitutable by the fluorine, as far as within the halogens go. That all comes down to one of the common things that we talk about, and when I ask you why, the answer is lower energy. So whatever makes the strongest bonds, if we make that bond, that will be the lowest energy.